morning. Thank you so much for your patience. Apologies for the delay. We appreciate you bearing with us, and it's really wonderful to have you here. Welcome to today's Science Talk. I'm delighted to be your host, and we're really pleased that you're joining us for this session on assessing water policy interventions, a stakeholder-driven multi-scenario approach for regional adaptation. This talk, like all others, will be recorded, and the recording will be made available after the talk on our YouTube channel and our website. You can watch the entire 2024 series as well as the 2025 series on our website at unu.edu/INWEH/science-talks with an S at the end. We'll also conclude with an interactive question and answer session. So please put your questions in the Q&A box, and I will be sure to read them out to our speaker. And now it is my great pleasure to introduce today's speaker, Dr. Mohammad Reza Alizadeh, who's a research fellow in human and environment system analytics. And his research addresses global warming and environmental changes using a range of multidisciplinary approaches. His work encompasses a wide range of areas, including analysis of climate issues such as heat waves, droughts, wildfires, as well as the development of models that integrate climatology, hydrology, and remote sensing. His expertise extends to human natural systems, integrated dynamic modeling, decision support systems, and the coupling of socio-economic and hydrological models. His work has been recognized with several prestigious awards, such as the Banting Postdoctoral Award from the Government of Canada, the Best PhD Thesis Award from the Canadian Society for Bioengineering, and the FRQNT Postdoctoral Research Award from the Government of Quebec. He has also received the MIT Leadership Fellow Award at MIT, recognizing his fabulous leadership qualities. Besides his role at UNU-INWEH, Dr. Alizadeh serves as a lecturer at McGill University, where he received his PhD in bioresource engineering and is research associate in the Department of Civil and Environmental Engineering at Massachusetts Institute of Technology. And with that, it is my great honor and pleasure to turn it over to you, Dr. Alizadeh. Are you able to hear us? Great, excellent. Glad to have you back. Are you able to hear us?
Yes. Yeah,
Fabulous.
I think something happened, yeah.
Okay, oh, that's great. Well, I just introduced you. So with that, I'll turn it over to you. Would you like to share your slides?
Yeah, sure. Let me. Are you able to see my screen?
Yes.
Yeah, is that good?
Excellent. Yes, and it's in presenter mode.
Okay. So thank you so much, first of all, and sorry for this delay to be connected and technical things. And I'm really happy to be here. Thank you so much for joining us, and thank you to all my colleagues at UNU to organizing this really nice and informative types of series for Science Talk. And I'm happy also to present and be as a part of these presentations. So as also Miriam just mentioned, I want to talk today a little bit about the water policy interventions and how this will affect the regional climate change adaptations, especially in developing countries, with a focus on how the stakeholder informations and inputs can really help to come up with the solutions and policy interventions that can help us. So is my clear and my slides, my voice and slides are clear, and are you able to see everything? Is that good?
Great. I see and hear you perfectly. Yes.
Okay, good. So just let me put my timer also not to go too much. So in this talk, I talk a little bit about the background and motivations, and then I start with giving you a real example of a coupled human water systems. What is that? And then talking about a little bit about the stakeholders, how this is connected to a coupled system when we talk about it, and then specifically how developing a model can help us to understand better these interactions between a natural system environment and also a coupled human system. And then we talk about the policies and also the future research that can be in this area. As we probably all of us heard and know, the human changes to ecosystems have created an area and a period of time which is considered as anthropogenic biomes. And by this, it means that the people and the human all over the world now are changing the land's use. And by this, we see that the human activities now has influenced really many ecosystems all over the world, and the dynamics of these ecosystems, in addition to climate and hydrological systems. And by mean, if you look at just this map, you see how the croplands and forests and the wildlands now are distributed, and especially the places that humans are settled, and now they are changing the lands to different types of the ecosystems, especially to crops and also agriculture. And by all of this, the IHS, which is the Hydrological Associations, they just called it as a decade of the Panta-Rai, which means that the hydrology in society now are really more interacted and compacted by these changes. So about 1/3 of the global lands and surface are transformed between 1960 to 2019. If you look at these maps, the red areas and also the yellow areas shows the net changes, and it says the single change and also the multiple change events mean that all these areas have gone under significant changes in terms of the land use change. And specifically the areas, look at Australia, for example, some part of Europe and also Africa, even in Asia, we see a lot of changes in terms of the land use change, specifically for agriculture. And when we talk about it, we see that the irrigation and the irrigated agriculture is the world's largest consumer of the fresh water in the world. And this means that by irrigation, we are only producing around 40% global food that is coming from these lands and types. And for example, in the US, around 65% of the total groundwater, which is withdrawn from the aquifers and also in this area, are used for irrigations in the US. So these maps actually shows us how the changes of the land use and also the irrigation specifically as a consequence for the land use change is affecting the whole base systems and also our water systems and water resources. Um, for using these hydrological systems and agroeconomy systems, when we talk about the society, actually it's a really complex and dynamics that are influenced by both natural and human, and also the climate variability, water management practices, economy, and also the policies. So, for example, as we all know, this is a really something that we see every day, how the natural systems can affect in terms of the climate. And also, on the other hand, we have these human systems, how we react to these natural systems. For example, by productions, when the population is increasing, so we need more food, we are just cultivating more lands, with intensified agricultural activities. So this is bringing us more land use change. And all of this, in consequence, is changing the hydrological systems. On the other hand, we are seeing that the intensification of the water cycle all over the world, which means that we are seeing now more extreme conditions in terms of the droughts and floods. And in a loop, all of these are kind of like toward a really situation that all of these systems are even more connected and connected. And for example, for the hydrological change, as I said, the drought, flood, and natural hazards are now more frequent, more intensified. On the other hand, human changes, the hydrological regimes, which we know as Anthropocene, and this is affecting the water management, land use, and irrigation. And basically, based on these schemes, the people say that the hydrology shapes the society, and at the same time, this is the society which is shaping the hydrology. And if I want to focus on this part and give you a little bit more information about that, we have four phases of the coupling between human and environment interactions, like until the mid 20th centuries. The people actually, more the scientists and also the community, they were looking at the effect of the water on the people. And this was mostly considered as a one-way interactions, meaning that, for example, the people were really interested, and also there was a lot of literature on this, that the people look at how the droughts, for example, or a flood events in impacting our society. It's more about the effect of the water on people. So in that area, we started to build dams, for example, to protect flood, to protect droughts, and many other interactions that is coming from the people in response to the environment. And here specifically, I use the water because my talk is more focused on the aspect of the hydrological system of the environment when I talk about it. But it can be, expanded to any other ecology, biology, and many other aspects. And from mid-century, we have another movement, which is environmental movement. In this time now, the people are looking at how people are impacting water, and this is the time that we started to look at, okay, when we do, for example, another way on the other side, people can also affect water quality, people can affect groundwater abstractions by, like depletions, the aquifers, and also the land use, the river restorations. And there are literatures a lot, and this part, for example, how the agriculture now are impacting the soil salinity, the water quality in the lakes, in the rivers, and many, many other impacts in terms of the quality and quantity. Later on, we have from 1990, the integrated management. This is the time that if you look at the papers and literature in that time, you see a lot of terms, for example, integrated water resource management, integrated flood risk management, and many other types of this terminology as called as integrated. And this is the time that the people, the community, and the scientists talked and considered that, okay, this is not just a one-way interactions, this is two-way interactions. People can affect the environment, and also the environment can affect significantly the society. So this is a two-way interactions, but still not coupled. And I'll talk about it, what we mean here by coupled. So in this area, we developed many models, which at the time were really also useful to look at how these two components, as the society and also environment, for example, water here, can affect each other. And recently, in 21st century, we are now talking more about the coupled model. So the coupled model, when I say a coupled model, it means that a new advanced types of the integrated model. But specifically, when we talked about couple, it means that we are seeing two-way dynamic interactions. And this is the big difference with any other types of the model and concept. We already talked about that. And when we couple, we say coupled model and the dynamic, what does it mean? And in the rest of the talk, I'm going to give you some more example about that. And understanding specifically interplay of the people, and for example, the flood, the droughts, how does it work? In this case, we talk all of this. This is not a new concept, but actually the way that we are looking at that and to update our models, assessments, and everything actually put us in this frame that we talk about the coupled and dynamics model. So let me give you, for example, an example here as a coupled human environmental system, and specifically I want to talk about human drought interactions. On the yellow part of this diagram, on the left side, you see we have some drivers. They are climate variability, as we know, like we have intensified droughts or flood or any kinds of things. Here we talk about less water, which is drought. So based on the climate variability, we see meteorological droughts, which means that less precipitation than the normal average in climatology. It can be 10 years, 30 years, but we have a drought situation. And then in this phase, we see the hydrological process and drought, which we call as the less average amount of the precipitation. And this means that the consequences is that we're going to have the soil moisture drought, which is a kind of agricultural drought rather than the meteorological drought. And then in case all of these result in hydrological drought. And then at the end, we see the ecological impacts in terms of agriculture and many other ecology consequences that we see. But in any stage of this drought condition, as you see, there are human activities corresponding to any of this. When we see the meteorological drought, the people start to do the land use. For example, to face this issue, the society try to respond, and in any stage there is a different stage response. And for example, we see the meteorological drought, we see the land use, and then we have the soil moisture drought. We start to irrigate our systems because we need more water conditions for the root zone for the plants. And then we start to build dams to have more water when there is a dry season in the summer, for example. And then we, at the end, when we don't have that much water in our dams, we start to abstract the water from other resources, for example, groundwater or any other resource that is available around us. And like these responses and consequences, they are all really tight. And the couple model actually try to see these interactions and look at any of these components mathematically with the dynamic equations and to look at all of this. So when we talked about the couple model, actually, we are trying to understand all of these components in more detail. So up to now, I just wanted to give you what is talked about when we talk about the coupled human water model or a human environmental system, what we actually means, but how this coupled model, human natural systems, can help us to react for the future disturbance and adaptation uncertainties. What are the benefits rather than a traditional hydrological model that has an input and output? For example, you put some data and variables and you get out. So what are the benefits and advantages and how it can help? So now we want to discuss a little bit about this part. I have three main subsequent questions that I'm trying to answer here. First of all, how will climate change affect this coupled human water food nexus? And what can be done to improve this resiliency of the natural resources and human systems? What we can do actually, and how and here integrated socio-environmental coupled model. I use specifically integrated and coupled to show you the coupled and also the integrations can help us for the making adaptive decision relatives insights in terms of this. So for all of this, these projects was a really big projects about the 7 to 10 years projects supported by the government of Canada. They had different case studies and places in the world to look at this. One was in Canada, one in Guatemala, one in Germany, and one in Pakistan. Basically, in different types of country, from developing countries like Guatemala, Pakistan, to really develop like Germany and Canada, to see these interactions and study all of these components that we're going to talk. Here in this talk, I just focus on Pakistan part and give you some examples and results that we gathered. Many people work on this, including myself. Some of these projects was as a part of the PhD and also some part of the postdoc and research scientist roles that I was working with my PhD institutions and also at MIT. And this is still an ongoing project in Guatemala and Pakistan, and people are still working. We are connected. There are many people in Pakistan Council of Water Resource, Zakaria University, NSERC in Canada, and also SSHRC. For the Pakistan, to give you just some context about the area, if you're familiar with that part of world, we have Pakistan, and in this area, if you're able to see my mouse, so in this area we have these really high mountains of the world, Himalaya, and we get a lot of snow, and there are some like snowpacks and ice that generates a lot of stream flow that comes along the country in Pakistan and then goes to Indian Oceans. And so there are availability of the surface water, and specifically this was the case 20, 30 years ago before this climate variability and intensification. So the government and the people, because of the availability, started to build a lot of canals for irrigations using this surface water. So if you go to that area, you see that it's one of the most intensified irrigation systems in the world. Around the 77% of the area is cultivated, and it's one of the world's largest continuous irrigation systems. There is a really deep human water nexus. And by that, I mean, there is water. People are really dependent on the agriculture. So whatever they cultivate, they use it for their human life. They cultivate rice and wheat mostly, and they just use that for their life. So between agriculture, water, and also all of this is a really deep connections. And there is a large network of canals and also tube wells in that area. But after some years, there has been a lot of significant changes. First of all, the soil salinity and groundwater depletions that I talk about a little bit, and also because of the uncertainty, for example, from the climate change, from socioeconomic conditions, population growth, and also policies. If you look at this map, it shows some of the conditions for the water logging and also the number of the tube wells from 1950 to 20 around 18 on the x-axis, on the y-axis on the right, you see. So the orange line and the blue lines, first the blue shows the water logging area. It's an index to show how the surface water with these canals are used in that area. And as you see, first we see a period of the canal irrigations and rising groundwater table. And because of that, we see the problem of the severe water logging because there is excess water and the people use it. So the groundwater table comes up, and then we see that. But based on the uncertainty from the climate change, we talked about it, then we see a period that there is really growth of tube wells, and this is the time that the surface water now is not available, and we have the agriculture activities and need the water to continue, and there is no water, so the people start to use the groundwater, and that's why we see a sharp increase in the number of the wells. And when I say tube wells, there are really small wells that they are not really deep, around like 15 to 14 meters sometimes, and they use all of this water. But now this is not the situation. Even we are seeing really more deep wells, even to hundreds, that the people are extracting water. So all of these conditions, if you look at this, the water productivity in Pakistan compared to even countries with the same socioeconomic condition is really low in terms of the how much water you use to produce actually the areas. And also, if you look at the crop yields that the water is used for example, the wheat and rice is kind of the same. The Pakistan is really in the middle of the like in a really low performance in terms of the crop yields, and that little star shows the average for the world. So this is the conditions. For doing this, we started to talk with different stakeholders. So we started with a stakeholder analysis. We categorized them. A typical stakeholder analysis that most of you probably are familiar even better than me. So we talk with authorities, we talk with land reclamation departments, soil departments, water departments. We talked about different policies and also issues. We talk with decision makers, the Ministry of Agriculture, local governments, many other people, implementers who are affected and impacting, for example, water management departments, and also the people from the area, the farmers, domestic consumers, and organizations, NGOs, through a methodological framework that I don't want to go through all of these details, but we just frame our problem. We asked our stakeholders. We designed the process. We did individual models, group models, and then using the participatory models that I'm gonna give you some information. For doing this, we try to look at the participatory modeling approaches, and with the focus of storytelling. There is a slightly different approach when we talk about the storytelling methods for the participatory, and this means that letting people to talk about their memory of the system, which is very important, rather than just some predefined questions that you cannot actually gather the most information. So they all feel free to talk about many aspects of the systems, and when we talk about the system, this is the purpose to look at this as a couple model. They can go from economy, society, policy, water, climate, and many things. And this is the responsibility of the people to extract that information. So we did that. We talked with the people. We had different workshops from year 2019 to 2023, several years interviews, and then we developed causal loop diagrams. We allowed them to talk about optimistic and also pessimistic and also realistic conditions with the perspective theory and many types of these social science approaches that at the time I was not also very familiar. We had some expert in that area, and also I learned a lot about that, and I tried to apply some of this in our approaches. And then we came up, as I said, with the different storylines. As an example, I just give you 5 storylines here that we thought these are the most common storylines that you can define for the systems. And when we talk about it, it means it gives you a kind of holistic overview, the whole systems, in terms of the what has been done and affected the system, and what are the outline and the window for the future from the perspective of the people that are in the systems. And so these are the qualitative storylines. Now our responsibility is to make them quantitative, and we are engineer, right? So we want to model them, we want to change them to numbers. So there are different processes and many approaches. We use the individual stakeholder interviews the way that we did, and then we developed causal loop conceptual models, and then using the linguistic variables interpretation approaches, we defined membership functions. I'm going to explain a little bit about these approaches in the next slides. And then we came up with uncertainty bounds of these drivers of the systems, and then We also use multi-level perspective framework, which considers the micro, macro, and also meso levels of the people, like in a very small scale to also a really large outlook of the systems, all of this with the expert, like the farmers in the system, and also someone who is a decision maker, let's say the ministry that is applying the policies. And for doing this, for example, when you talk to a farmer, let's say he or she doesn't have any sense of the variables. They are just talking about the linguistic variables, like let's say change in irrigation area in the past 30 years. They give you some information about high decrease, low decrease, for example, intense changes. So then using, for example, a simple membership functions, fuzzy actions, you can just, quantify any of these expressions to linguistic values. So we used center of gravity approach, and then we try to gather any of these memberships can come from a group of the people, for example, decision makers, engineers, expert, NGOs. So then you can just sum up all of this together and look at them, and then come with the center of the gravity, and then look at what that values means. For example, it's, if someone say in the system you see low decrease of something, then you're able to change it to a real value, a number for your model. So then based on all of this, you can come with the uncertainty ranges for the socioeconomic and environmental drivers of the systems. Again, it's just an example because of the time limitation. I don't want to go through all of this, but I would be happy to let you know if you have any questions about this. So the most important part is that at the same time that we had this stakeholder analysis on the field with the people in the area, which is actually the left side of this figure, we have also these global scenarios named as SSP, RCP that we all know from ICP. So based on this scenario, we have an overview, an outlook for the future, for example, by the end of the century in terms of the changes for our climate systems and also socioeconomic systems. But you really need to downscale them. The idea was to connect all of this, like the global and also the real storylines from the people in the field and in a regional scale. So to combine and put them together and to come up with a more kind of downscale. So this is why we try to link stakeholder storylines with global shared socioeconomic pathways. And for doing this, we did one-to-one mapping. This is a really, sophisticated approach that we try to look at the context dependency, ambiguity, subjective judgment, many other aspects of all of these, like scenarios, the local scenarios and also the global scenarios. We try to look at the equivalency, coherency, consistency, but at the end, we had some, we call it as a localized or downscaled scenarios that gives you two really important aspects. First is the perturbations or the shocks in the system. So you can see how, for example, population change or climate change, for example, a drought or flood is impacting the systems, which is downscaled, and also the adaptation policies, what people think in terms of the policy changes or investment that can be done to fight and also to face these changes, for example, the technology innovations, the behavior shifts. So these are all the inputs for us, and then we are able to model. And for the model, we also developed a coupled socioeconomic and environmental dynamic model. This is also a really sophisticated model with a lot of compounds. For example, here we have five sub modules. One is for policymaking, one for agriculture, economy, environment, and water. They are all interconnected using system dynamic models that if you change any components of any of these submodules, you will see the changes in any of other aspects of the system. And this is based on a socioeconomic model that is coupled and linked with the hydrological model, a physically based model. As I showing here, this is a distributed model, and this is just a watershed in Rachna Doab region in Pakistan that we are looking for. And also, so as you see, this is a distributed model. We are able to look at the groundwater, soil salinity, surface water, all of these hydrological and environmental variables. And at the same time to see, for example, if you change groundwater here because of the drought, what does it mean in terms of the, for example, the available water, and what does it mean in terms of the farm income, and what does it mean in terms of the crop yield, how they are connected and how they will impact each other as a consequences. So this is the model. So we had also the input, as I said. So we tried to look at all of this. First of all, as a result, one of the important thing is that uh, from what we understood from this modeling approach, we saw that the stakeholder discussed that the environmental and natural resources are the most important component that can change and impact on the system, which makes sense as we also expect if there is a period of the severe droughts, or for example, we have higher than average precipitation in the area, you see that the system can react to that. So that makes sense. But interestingly, the second important part here is policy and institutions effect, which is around 22%. So after environmental and natural resources, this is the policy that interventions can really impact the systems, and also many other things, economy, human development, and technology. These components are coming from the main aspects of the SSP scenarios, but here in Pakistan, these two parts are very important one. So using this model, we look at the groundwater depletion on the x-axis from 2020 by the end of the century. As we see, the population will increase based on this line that shows the trend, but water storage is consistently decreasing per capita storage. So we're going to see more severe conditions in terms of the water availability in the systems by even around 50% decrease by the end of the century. And if just look at the groundwater depletion based on different RCPs in terms of more intensified climate change, RCP 8.5, you see that at the end of the century, by 2050, actually, you will see even around 70% by the uncertainty groundwater depletion in the systems. And if you look at the watershed status, you see that the groundwater level will change in different parts. It's not also uniform in different parts. For example, in the west part of the area, you will see even more. This is because of the conditions in that area, that the extractions even is more. And we also looked at the crop yields in the area, two important crop in the area, rice and wheat. So around 20 to 40% decline on average for rice yield due to the climate change based on RCP 4.0 and 8.5. Any of these lines define one of the storylines, the five main storylines that I showed you and I discussed with you a little bit. SSP 1, the downscaled one, to SSP 5 in terms of the crop yields, but on average, you see around 20 to 40% decrease. The same conditions for the wheat, around 15 to 20% decrease up to 2050. So you're able actually to look at any of these components in these models, in the coupled model, We looked at the soil salinity conditions, and again, the soil salinity condition is more uncertain. We see some really significant change to even some decreases. This is really an uncertain variables, but in general, you can see that in some cases, even for example for SSP5, at the downscale valve, there is a sharp increase after 2050 for the soil salinity conditions in the area. So in general, I just want to show you that how these models, developing the models with these humans and the stakeholders can give you some idea about different aspects of the system. You can talk about the water, groundwater, you can talk about the economy in terms of the crop yields, you can talk about the environment, soil salinity, for example, to see how all of these components can be affected. But what we can do for this part, so we try to look at the resilient, robust policy development in the area. I will go quickly just through some of this. Just to give you an idea, for example, this is a functional responsive curve that shows the status of a systems. When there is a disturbance in a system goes to a different disturbances phase actually. And so according to this, we defined 5 resiliency metrics in our systems. First of all, the time of recovery. If, for example, a period of the drought, how long does it take that the systems goes back to the initial resilient systems? What is the rate of return? What is the degree of the return? How fast it goes back? What are the post-disturbance perturbations? What are the corrective impacts, meaning that how the systems will impact? What is the ability of the system to go back to the initial resilience? So using these resiliency metrics, we looked at different objectives of the function, farm income, groundwater depletion, soil salinity, and policy reliability to see how these systems will affect. I just want to go to allow you to ask questions. So this is just a trade-off example of these objective variables. So you can come up, this is a typical engineering actually approach that you use a multi-scenario, multi-objective optimizations. Any of these lines is a policy interventions in terms of these 4 objectives that gives you how, if you choose any of this approach, how your groundwater, farm, soil, and reliability will affect, and that these spheres also shows the reliability for any of these scenarios that we had. So we looked at all of this, and the result is that if you look at the groundwater and farm income, for example, as you see here, the groundwater never goes back to the initial status. If you look at this line here, which means that the initial conditions and a status, so there are uncertainty in terms of different variables, and this is up to 2050, and probably the main reason is that the groundwater is a really slow variable, meaning that it's not affecting, is not actually responsive very fast, even if you improve the systems. But at some case, the farm income also can come. So and any of this, for example, the return period and return time recovery, if you look at the SSP4, which is the scenario based on the, so some of these can give you a better outlook. You can get a better performance in terms of how the systems goes back to the recovery time, but there are also some scenarios that are really worse in terms of getting back to the initial phase of the condition, for example, SSP3. So with all of this information, we talked with the stakeholders, and ask them, okay, what would be the best approaches, for example, in medium to long term, and also in short term, to come up with some solutions for the systems to improve them as a potential policy interventions. So they, based on the stakeholder analysis and also the discussion that we have, they provided some possible solutions. All of this information is coming from, again, this our storylines and storytelling approaches with authorities, decision makers. They gave us these some of the solutions that I'm just listing them, some of them here. For example, doing a canal lining, building some new reservoirs, improving the irrigation systems, trying to harvest the rainwater, water banking, promoting salt tolerant and low water crops or canal water distributions, building new ones. So specifically, I just focus on these three specific canal lining and reservoir construction and irrigation system improvement. We input all of these policy interventions in our model and systems, and it shows up these three policies can have a slightly better performance, and I just focus on these three for now. And so if you look at this, for example, in terms of the crop yield, um, if you don't do anything without any investments, compared to if you apply any of this policy in the system, for example, you do the canal lining, you build the new reservoirs, or they improve their efficiency. You see that with the simple uh, improvement in irrigation systems in area, there is up to even 20 to around 15% increase in terms of the crop yield, up to 20-50 years. If you look at the fresh groundwater net recharge, kind of the same compared to no investment with applying these three policies. And as you see, the irrigation efficiency also is one of the good, really simple approaches that the policy and authorities can adapt, and also for the reservoir constructions. And for the soil salinity improvement, also, you see irrigation efficiency probably is not the best, but canal lining, which the government has started doing this in recent years, can really improve the systems a lot in terms of the soil salinity. So using all types of this information, I just wanted to give you a very simple example of how a coupled human water systems can be modeled, how you can approach, for example, a real world problem, specific area, and to see how the climate change is worsening. Basically, as a results, we see that the groundwater depletion, for example, in region Doab in Pakistan, is accelerating. We are seeing increasing soil salinity, reducing crop yields, and also lowering farm income. But implementing really straightforward and practical policies, as I showed, for example, just improving irrigation efficiency can have a really significant improvement in the systems. And stakeholder engagement is really crucial for understanding all of this, to have a better idea about the practical solutions for a human water food system and potentially improving them, and also the capability of the coupled socioeconomic models and environmental systems that can really help us to understand better human environment interactions for sustainable decision making. I wish actually I had more time to talk in more detail about my results, but because of the time constrictions, I wanted to stick that we finish at 11. I also want to thank my colleagues at MIT, at McGill, my advisor, the people who were working in Pakistan, and also my other colleagues at UNU that help us to actually be able to do this research. Thank you so much, and I would be happy to take any question.
Thank you so much. That was really excellent. Clearly a lot of very impressive work in combination of different types of methodologies, stakeholder engagement. So really congratulations on this important work. Thank you so much for taking the time to share your research with us. I guess my first question, which I'm hoping might allow you to, I thought I saw for a split second a slide, which was kind of what I wanted to ask you about. So I was wondering how equity considerations factored into the different storylines and how social human vulnerability could factor in. And if that was something that you were going to talk about in your last slide, that I welcome giving you the opportunity to talk about that.
Oh, sorry, I think I missed the first part of your question. Can you say it again? Sorry.
I was wondering about equity and social vulnerability.
Oh, yeah.
How that, yeah.
Yeah. So yeah, I mean, I wanted to actually talk more about it, and I also had in a slide here. The whole idea about these types of the models and like the coupled models is exactly to come up with the vulnerability and resiliency of the systems. I a little bit talked about the resiliency approach that they use and also this the vulnerability. So with all the information that you can have, specifically with the advancement in the large language models and also specifically the availability of different types of the data, for example, from the remote sensing, you can overlay any of this, and then you can come up with the agroecosystem vulnerability, meaning that you are now able to see which parts of the world are more vulnerable to flood or drought or wildfire or any of these parts with this information and data. And then using the information based on the other like aspects of the resilience, climate resilience adaptation plans, you can use such models that I just introduced here as a coupled model to come up with public awareness, education, adaptive management, and water use efficiency. For example, in some of my slides, I showed you, I wanted to actually talk a little about this, but for example, here in when we talk about the groundwater, you can basically and spatially see which parts of this watershed. This is a relatively not a very large, but let's say in a global scale, you're able to see these parts are more vulnerable in terms of the groundwater and the social vulnerability of the people who is living there. What are the categories of the income for these people? What are the other aspects and social, like vulnerability of these systems? And then you're able to look at all of this, and this is the goal actually for using this model. That was the idea, just like very shortly to just state it. Yeah, and thank you for bringing up this.
Thank you, Dr. Alizadeh, for this very useful presentation, informative
Thank you.
and perspective. My question is about the vulnerability slide you just presented. And I saw a layer that related to healthcare access. Yeah.
Yeah.
How this has been integrated within this modeling system.
Yeah. So in this case, for example, in Guatemala projects that I didn't have the time to discuss it, we looked at different types of the vulnerability in the people. And when I talk about it, for example, if there is a water quality issue in the area, how this will translate for the impacts for the elderly people compared to the, for example, the young group of the people. And this approach, this social vulnerability can be used in different contexts. For example, in another research with my colleagues, we looked at the wildfire vulnerability impacts, and also this is the case that you can also use it in water quality, water quantity aspects of the system. And as I said, there is a really deep nexus between water, agriculture, and society in such like coupled systems, specifically in developing country. We are very familiar, like in Iran, Afghanistan, Pakistan, the people are really dependent on agriculture. And when there is a drought for this season, this means that you have less water, then your yield, your income, everything is impacted. And then this translates to many other aspects, for example, the social life of the people. With that information, looking at that, the demographic, the topography, the health access, the economy indicators of these people, when you overlay all of this information, then you can come up with an index for the vulnerability, and then you are able to assess how this probably can affect the agro ecosystem's vulnerability in general.
Thank you so much for a fantastic presentation, Dr. Alizadeh.
Sure.
I was just wondering about how can you talk a little bit about how these types of models are validated? One, and then I'm just wondering also if you've developed in within African.
Sorry, what was the last part? Sorry, there is an interrupting.
Wondering if you've developed any such models within African context.
Oh, yeah. Okay. So, yeah, for the first part, thanks for the question. For the first part, these types of the models, because this is a new generation of the model, they have two parts for calibration and validations as the typical and traditional models. So we actually have a really one phase of calibration and validation, and we have a paper on that showing that how these models have been validated. So first, we used like any of the models, the training and testings portion of the data. For example, we used the year from 2000 to 2010, 10 years of the data, and didn't give this information to our models just to be able to reproduce all the informations that we expect if the model is able to reduce them. So then we did the calibrations in terms of the calibration for the parameter of the variables and also the outputs of the variables. And also we did then the calibration and validations. But at the same time, since this model have a really socioeconomic components, it's not that easy to look at some of the parts. For example, you don't know what's going on in terms of, for example, the farm income in 2-3 years. This is not a value that you can see really fast. In that case, there are another types of the calibration validations in terms of the trends and more long-term approaches. So then you are able to see the different, it calls that the behavioral calibration approaches. So then you are able to see if the model is able to reproduce a long-term shock and also the consequences. And we did that. There are lots of information that you can use that. But this is something that many people now are still working on, that to improve this phase of this coupled model, to improve the calibration and validations. But that's a really important point, as you mentioned. Yeah, but our model were actually very, like in detailed and carefully validated. For the second part, for Africa, we hope to do that before, but based on the limitations of the funding, we wanted to start that part, but based on these changes and everything and uncertainty about the fundings and everything, we are not doing that. But we hope to have a new proposal to look at some of the developing countries in that area and working with some people, and yeah, hopefully we can do it soon in the future. Yeah.
Thank you very much.
Yeah, sure. Thank you.
Fabulous. Thank you. I think we'll also have to have you back to learn about the Guatemalan research as well as Canada. I also wanted to highlight that another one of our affiliates in the head of the hub in Hamburg has the first global map of soil salinity. This is Professor Dima Shokri, who has the AI for soil science. So it seems like there are a lot of really interesting areas for collaboration here.
Sure.
Thank you so very much for your excellent talk. Thank you to all of our listeners. Thanks for bearing with us as well. Really appreciate your taking the time to be with us today. And we look forward to both welcoming you to Richmond Hill. Hopefully, see all of you, seeing you again. Thanks very much.
Yeah, thank you so much again. I really appreciate for providing this opportunity, and also all my colleagues. I really look forward that we can collaborate on similar projects. And as you said, there are many close connections to all other projects. Thank you again. Yeah. Thank you. Have a good day.